We're going to go to our next speaker, Dr. Baosen Zhang. He's an associate professor in the Department of Electrical and Computer Engineering at the UW. He holds the Keith and Nancy Ratty Endowed Career Development Chair. He works in various areas of power and energy systems, from hardware to control and learning algorithms.
All right. Okay, all right. So I'm very happy to be here. Thanks for the invitation. My talk will not be as colorful as the last talk. I'm sorry, I don't have all the nice numbers to show you. So this will be a more technical talk on, looking at the energy system and AI, how they influence each other. So as was said, that energy, actually, you look at the power system, it's a quite interesting time in power systems. The system was relatively stable for 40 years. In the last 20 years, since suddenly started to change very fast. We're at a case where both on the demand side and the supply side, both sides are changing. And things are creating a lot of, the supply is starting to be uncertain as renewables. And then demand is really starting to pick up. So it's an interesting time to work in this area. And if you look at the opportunities and challenges in the area, that power system is a system where building big things tends to be challenging. As we heard, we're getting better at building plants, but building things like transmission lines still takes years and years to get there. But what is happening is the things around the grid, from data to control to smaller generation, all of these things around the edge, we can do them very fast. We can build them in scale of, say, months instead of decades or years. And with data, of course, it comes a lot of excitement on using AI and ML. How do we use this data? What can we do with this? And power system is a case that you don't get to try things out, right? You fail once, they'll never talk to you again. So you have to make sure that anything you do, you don't get to say, oh, I'll improve, let me try this 10,000 times, I'll get better. That's not what you can do, right? You cannot fail. And then now things are sort of start to interact. We used to be, a couple of years ago or 3-4 years ago, is how do we use AI to improve the power system? Now AI is becoming one thing that power system engineers think a lot about, just to power AI that's coming in. Okay. So in this talk is, one thing to remember for a power system is we have to balance the system at all time scales. So supply has to equal to demand at every second, every minute, every hour, every day, every year, every decade, and so on. So it has to be balanced across all time scales. And AI, does help us to solve some hard problems and also create challenges along all those time scales. So I'll give you 2 examples, one at a very fast time scale and one at a much longer time scale, of how AI comes in, how it can help us to solve some sort of very hard open problems that we had, and what new challenges creating for us. So this is an admittedly very biased overview. There's a lot more things going on than what I'm presenting. So there's just a couple of examples of things we have done. So let's look at, first at the fast time scale, this thing called frequency control. So frequency control comes into the fact that if you think about power grid is a very large network system, right? It's sort of thought as the most complicated engineering system ever built. And the question is, why do lights stay on? It's a surprisingly non-trivial thing to answer. Because disturbance in the system happens all the time. You can flip a switch, you can plug something into the outlet, you can turn off a light, and so on. You don't tell anybody this. You don't tell the generator, I'm going to use more energy, right? There's no explicit communication. How does the generator know this? Like, I'm a generator, I'm a hydro generator 1,000 miles away. What do I know what's going on? Yet, power stays on most of the time. Things are balanced. How does that happen? This happens by a mechanism called the frequency control. So I want to explain this a little bit and then tell you how renewable is changing this and what AI can do to help us. So supply and demand is basically maintained by just reacting locally to a thing called frequency. So if your supply and demand is balanced, basically in the US, our grid runs at 60 hertz. It's a constant frequency. If you plug something in, demand goes up, and then frequency goes down. So you can think of, so you're borrowing this rotation inertia in the big generators. You're borrowing this power out of it, so they spin a little bit slower, and then this power goes for the demand. Then if your generator, you observe this, and you're supposed to do this for feedback control, and you can recover your frequency. And this number tells us basically the health of the grid. So a single metric that tells the balance. And if you have big generators, then they sort of do this linear response. This is determined by the physics of machines. They just rotate this way. The question now comes, what if I replace all these big synchronous generators with power electronics, right? Most renewables connect to the grid through power electronics. These are digitally switched circuits. They have no physically moving part at all. So they don't need to do this response. They have no natural response to this. And then somebody mentioned FERC. What FERC does is FERC tells you, well, you have to do something. Otherwise, the grid falls apart. FERC doesn't tell you what to do. Just says, oh, I require you to do things. So the grid is stable. And then, what should you do? Well, one thing you can do is maybe you can try to act like a generator. That turns out to be not a very good strategy. So if you want to think about a big synchronous generator is the size of this room, your inverters are this big. So if you try to be a synchronous generator, you're not a very good synchronous generator. So you should do something else. But this is actually a very hard technical question. We don't know what to do. We don't know how to solve this problem. So then the obvious answer to that now is, oh, let's use AI for this. Let me just, I don't know what to do, right? I'm just putting in a neural network, and hopefully it does something reasonable for me. And this is not very hard to train. So what you can do is, your goal is basically to optimize how large the oscillations are in the grid. So you can put this into a training environment. You can look at, okay, how do I minimize this thing? Takes you about a few hours to code this up. It's not very hard. And very quickly you figure out, hey, my neural network does really well. It beats out everything else. And gives you this kind of shape, like this is how you should respond to frequency change. It looks weird, but who are you to argue with machine learning? So this is what you do. The trouble comes, well, if you do this directly and you put this into a grid, let's say you actually put it in and simulate it, what happens? It will actually blow up your grid. Okay, so training looks very nice. You put in practice, you will have unstable grid at this point. So the challenge of using AI into for energy system control especially is you need to make sure that there are constraints you have to include when you use this kind of tools, right? So there's a stability constraint, not just cost. The grid should be stable all the time. So I'm not going to tell you how we do this. The upshot is that we certainly know a lot about the physics of power systems. And then if you try to use that to meet the capability of this for AI-based controllers, what you can find is we'll give you a criteria what they should look like. Basically, it should be this kind of increasing function through the origin, and we can constrain the neural network to be this kind of class. Then we can learn the right type of controllers. It actually gives us quite optimal controllers, which the one in the middle, there's no way humans could have designed that. But then we can guarantee it's actually strictly better for the grid we use that. And when you work on this sort of physical system using AI, it actually makes the problem a bit easier to deal with. So a lot of times when you do machine learning, you're worried that what if the problem or the system or data you train on is different than the data you see actually in practice, right? So maybe I train it on this kind of network. In practice, these two lines go up. And this happens all the time. Every line goes out all the time, power systems. What happens? Do they work? Turns out yes, right? So this is showing you that if I have a disturbance, if I have a line outage, whatever controller you learn is actually quite good. And then this comes from the fact that because we're working specifically with the physics of power flow, the power system, we don't need to worry about this kind of things. We can sort of guarantee stability for all situations. And then you can retrain the controller if you want to. Right? So this is a very nice combination of AI solving some first sort of open question that we had in power. And then because we're working in this very specific system, we can overcome some of the challenges when you apply AI to other problems. This is a very one good use case of AI. And then the next, I want to switch to a case where, let's look at longer time scale. This is sort of resource allocation problem and planning, and often takes form of this sort of called optimal power flow problem. So you can think of this as a problem describing as I have some loads, I have some generators. How much should each generator generate to meet the load? I want to minimize cost, subject to a bunch of engineering constraints. So voltage cannot be too low, line flow along line cannot be too large, and so on. So I have a bunch of constraints I have. So this is solved all the time. This is solved every 15 minutes, every hour, every day. We'll keep solving this. And solving a single problem is not very hard in practice. The way we have solvers that has existed for 40 years to do this. And if you look at this question, naturally you want to think about, well, I don't really know what my load will be. So how do I handle some uncertainties in this load or generation? Before, it wasn't really a problem. You have very small error in your forecast anyways. You just solve for the average, and you eat a little bit of the error. You have some reserve for that. If you have, say, 30% renewables, it's sort of really hard to forecast wind day ahead. It's really hard to forecast solar. You just have higher uncertainty. Then you cannot just solve for the expected forecast. You really have to take all these possible scenarios into account. So instead of solving one problem, every 15 minutes or so, it's now very hard to solve, let's say, 10,000 problems every 5 minutes. I just need to look at all through the scenarios, what could possibly happen in the future. Now again, if you look at this problem as a sort of very nice machine learning problem, because you can think of it as I give you some demand, you tell me what the generation is. It's some box that is a solver, but you don't need to care about that. So I can still replace that, say, by a neural network, and then say, OK, just tell me what the generation is. I don't want to do a solver. I don't want to use a solver. The sort of challenge here is, well, power system, we have hard constraints. There's a constraint you have to meet. So approximately OK solution isn't very useful all the time. You really want a feasible solution. That is hard to do. It's sort of hard to guarantee that your solutions are feasible. We have sort of made partial progress here. So for a sort of version of the problem, we can do this. So for a sort of simpler linear version of the problem, we can guarantee feasibility. For a sort of nonlinear problem, this is extremely active research. So I don't know, some folks from Microsoft are here, but Microsoft, for example, is trying to develop a foundational model for the grid, essentially try to solve this problem, so very quickly, right, very quickly. And even the approximately good solutions are useful for planning. So AI here has a potential to help us with very hard computational problems by speeding up computations in orders of magnitude. And if we can sort of ensure the property of the solutions, it'll be very useful with things we can use in planning, operation, and all those kind of things. And so these are two of the sort of success examples that we have using AI for power systems. Now let's sort of switch gear and look at what challenges AI load brings. And first, let's look at things in the seconds level. So this is a trace. This is real data. This is our data of training a version of GPT on one GPU. So what you see is you view this kind of very spiky load going up and down. If you zoom in, you have this sort of very large ramps just throughout training. Sometimes you have a large ramp going down. Sometimes you have a large ramp going up. Normally, we don't worry this much about the load because we assume that load will average out. Right? You use power sometime, other people use power other time. On average, this thing averages out. What's sort of new about this is, well, when you train this kind of large language models or large foundational models, they are synchronized. They all train at exactly the same time. They all start and stop at the exact same time. So instead of averaging out, this sort of just adds up on top of each other. And then you can pretty easily get, say, 200 megawatt steps going through your system every few hours or so. You have this big step. And our system do not like this kind of steps. This sort of, we want to avoid this kind of steps, and can pretty easily lead to voltage and frequency problems here. So this is one challenge we're seeing. Actually, this sort of stability challenge has nothing to do with overall power demand. It's just second to second what happens. We have AI in the system. Then next, let's look at sort of longer planning in years. There is sort of very different estimate for AI load growth. I have seen numbers going from 5% to 50% of all US electricity we use for computing. Probably somewhere in the middle, but I'm not sure what exactly number this will be. So there's a lot of, there's big gaps. But if you're a system planner, well, which number do you choose, right? I have to plan my system ahead of the time the load comes in. If there's a order of magnitude difference, well, what number do I pick? In addition to this, there's a lot of uncertainties in technology. So if you look at DeepSeek, so DeepSeek came out, and then these two competing papers came out. Sort of amusing to read the title of the two papers. They come out this was within 24 hours of each other. That came out, saying dramatically different things. Both by reasonable groups of people, right? So again, we don't know what exactly will happen. And if on one hand, if you bet wrong, say you don't build enough capacity for AI, well, you have no power. If you build too much capacity, you spend $2 billion on something you'll never use, right? So there's consequences erring each way. And the thing to remember is that it really matters when and where you use power, right? So we really spend most of our time worrying about that last little 2% of power. So if you can spread out your power usage, then it's fine. It's not a huge deal. But if everything is concentrated at this for a single second, then it's a huge deal. So we know that data centers have a lot of flexibility. They can shift their load around. The challenge, the question is, it's hard to put a number on it. Right? To integrate that with the power system planning, I need a number of how much load it can move around. It has been difficult to put a number there. So to conclude, there's sort of a lot of changes in this grid, and AI is coming in. And AI does help us solve a lot of problems, create a lot of challenges, but I don't think these are intractable. I don't think these are sort of problems you cannot solve. I think, as in this talk or in here, I think we're just beginning to understand this loop, and I'll conclude here.